Welcome to EE World. I'm editor Martin Rowe. Citizens Radio Broadcast Service, or CBRS, that unlicensed band from 3550 megahertz to 3700 megahertz in the US, shows promise for private networks in factories, stadiums, for logistics, and for other applications. Other countries have allocated nearby frequencies for similar use cases of cellular. As many of the news outlets have reported, consumers are calling 5G a flop, and that's because they don't see these other use cases that are being designed in for 5G. For example, private networks based on small cells could be the quote-unquote killer app that consumers will never see. EdgeQ, a Silicon Valley startup, provides silicon and software stacks behind the small cells used in private networks. EE World spoke with Adil Kidwai, Vice President and Head of Product Management, about implementing and using CBRS.
5G brings a lot of new innovations, and those innovations are not necessarily driven by telco only. Those innovations can be utilized by a lot of non-telco customers. The Disney Worlds of the world, the PG&E, the stadiums and schools, campuses, and CBRS releasing the C-band in 4G, now going to 100 megahertz bandwidth, even more in 5G, is kind of a game changer to proliferate 5G even further, right?
What is EdgeQ doing with its silicon and software stacks to make CBRS and CBRS equipment more accessible?
When we started this company, we figured out, we talked to a lot of those people. We went to the ports, we went to the airports, we went to these factories, and we tried to figure out what is the pain point that these guys have. And for sure, one pain point was, I don't want to be paying a lot of money to the carriers. I want to own my own network for security reasons, for cost reasons, for a lot of other reasons. And the second main important thing that we learned was, it was the small cells and femto cells which primarily serve these networks were designed with a bag of parts, meaning there are multiple components which needed to be put together to make a small cell or femto cell or picocell work, indoor or outdoor. So the first approach and this, by the way, impacts the time to market for the solution, because when you have to integrate like 10 components together, then you are debugging issues. This chip is not talking to that chip, and this software is not compatible with that software. So one thing which we did was we tried to integrate as much as we could into the silicon that EdgeQ has. You can go on our website and you can find out what components we integrated. We have integrated pretty much everything, from layer 1 hardware silicon to layer 2 to layer 3 to network processing unit to CPU. We've integrated all those things into one simple silicon. So that resulted in a lot of improvement in the cost, as well as the board area, the size of the solution, from the hardware perspective. On the software perspective, we provide a fully deployable software, which any, let's say, private network operator can take. For example, if you go talk to an IT manager in Disney World, she would know how to bring all these components together, because she simply has the experience for that, right? If you go to a PG&E IT manager, he wouldn't know this as well. So we position ourselves as a one-stop shop from hardware perspective as well as software perspective, that we make a chip and provide you a deployable software stack. And we work with ODM partners to make a box. We are not a box making company. We are a chip and a software making company. We work with a lot of ODM partners, and we do the heavy lifting of full hardware and software integration. And our ODM partner make the box and the PCB, and eventually it reduces time to market as well as cost. And all this is done on the C band, primarily on the C band, the N78, N48, N77, the 3.3 to 4.2 gigahertz band, pretty much.
EdgeQ's base station on a chip handles the baseband processing in a base station. Can you explain those functions?
We provide a baseband processing chip which runs layer 1, layer 2, and layer 3 software. So you don't need any separate chip in the box. Okay, it's just one silicon. We do provide the deployable physical layer software as well. For example, channel estimation, equalization, all 4G and 5G functions. And we interface with any third-party layer 2, layer 3 provider. You might have seen some press announcements last couple of months. One of them is Mavenir. We are working with their team as our L2, L3 partner. And to answer your specific question about RF, this silicon has integrated the data converters inside it. But for the down converter, mixer, and the low noise amplifiers, we work with RF partners around the globe.
Right. Okay.
So we have few RF partners. So this chip, along with the RF IC, together makes the baseband. We take full control of the RF integration as well. So our partners don't have to, put these two chips together and scratch their head, what's going on here. We provide them the full baked solution.
Your slide says 4G plus 5G plus AI. Can you explain the AI component?
AI and communication are not fundamentally different. Actually, a lot of principles of AI have been borrowed from communications. Both of these fields use very common mathematics like dot product multiplication, averaging, pooling, nonlinear operations. They are very, very common. The fundamental difference between AI and 5G inferencing is that communication or 5G and 4G works on complex numbers. AI inferencing mostly work on integer numbers. So we designed this chip based on RISC-V processor, which where I'm moving my cursor on. And we designed some basic mathematical operations which can be used by communication as well as by AI because the fundamental mathematics is same. Okay. So the way we see AI is AI can be, now I'm coming to your specific question. AI can be utilized in two ways. AI can make 5G better by doing some smart operations which can help 5G become a better 5G. Or 5G can make AI better. So we say 5G enabled by AI or AI enabled by 5G. Okay. These are two different applications. Let me give an example of first application, right? First type of application where AI makes 5G better. For example, you can do spectrum monitoring, interference monitoring, user monitoring, user scheduling. All this can be held by AI, right? You can have an AI model. If an access point or 5G access point is in a factory, you can find out at which point in the day there is particular spectrum being corrupted. And you can take preemptive measures to not let it happen. So in such cases, we have AI models which are helping 5G become a better 5G, to have a higher reach or to have a higher throughput. These are just one example. There are at least 10 more examples. On the other side of the applications, 5G can make AI better. For example, imagine a AI device on in a factory monitoring a process, and imagine that this AI, the images that are coming in have to be processed there, and some conclusion needs to be made that this process is not good or this particular equipment is broken. Typically, what happened earlier was that the data was being processed at the edge, and metadata was being sent to the cloud to make a decision in the central command and control unit. We enable that by merging 5G and AI together. where AI can do its camera processing or any AI model processing. And 5G, particularly 5G, because it enables ultra low latency, can help get that metadata from the field, from the edge device, all the way to the central command unit.
Are you using AI at the physical layer, the protocol layers, or across all layers?
This is physical layer, right? 5G massive MIMO scheduler, beam pattern optimization for massive MIMO. These are all physical layer functions. As soon as you go into giant channel estimation and detection, also physical layer function. We can also use 5G for massive MIMO beamforming scheduling, uplink controls, RRM optimizations, for example, right? So if you are beamforming and you know that the user is moving and there is a pattern of the user movement based upon the knowledge that you have attained over let's say, last 6 months, being there and making a model, then you can help a 5G scheduler schedule the user better.
If a person walks around inside a building, you can essentially get a model of the layout of that building. Can you apply the same logic to factories as well?
Primarily in factories, there are two types of user equipment, right? One is this guy who might be traveling, who might be walking around with a tablet. And there are a lot of machines which are fixed, right? These machines turn on and turn off at a specific time, or they are always on. They generate interference, for example, right? So not only human users can benefit from AI modeling, these machines benefit from AI modeling even at a greater length because they are static, right? So this is something that we are testing with a couple of our partners, where we are using the AI functions in this chip to model the environment and do two type of things. First is RF spectrum monitoring. Where is the interference coming from, at which point in time, and in what part of the day, such that we can tune the RF filters preemptively, such that that interference does not happen. Second of all, the scheduling of users, right? At what time during the day, for example, in this machine starts, it will need a lot of data at a very low latency, for example. So we model the whole factory floor, and that is where AI helps us to make 5G better. Mentioned AI enabled by 5G. These are the typical AI functions where, let's say, there is object recognition, there is a detection of or defect or leak detection in a factory, where you are just getting a lot of images from the camera, okay? And you have to make a very fast decision. And what we do is we process those images at the edge and send the metadata, just one or two text messages that, okay, I detect a leak on this pipe. And that metadata goes within a millisecond to the central command and control unit, and therefore they take the corrective actions. That is what we call AI enabled by 5G.
When you say edge, where is the edge in a private network?
We defined edge as one hop away from the user equipment.
Okay.
So for example, if I have the cell phone in my hand, one hop away is the edge. This cell phone could be talking to a Wi-Fi device, access point inside the building. That is the edge in that definition. Okay. It could be talking to a 5G box inside the building. That is the edge. In case there's nothing, no Wi-Fi, no 5G small cell around, it's talking to a base station, that becomes the edge.
Besides the EdgeQ chip and its software, what else do engineers need to design, say, a small cell?
It requires RFICs.
Yep.
Number of whatever band you support, and 2x2 or 4x4. It requires a Ethernet PHY, because eventually your data is going to go to the Ethernet connectors.
Okay.
And it requires some usual suspects like DDR, memory, flash, USB memory, USB, power management IC, and stuff like that. Right. Let me also share with you, while we are at it, the box that we have made, and you will get a feel of what a real box will look like with my chip. Remember, I was talking to you about that eventually there's a small cell box. This is made by one of our ODM partners, WNC.
Okay.
And this has a RF board. You see this RF board, and this is a baseband board, right? And a baseband board will look like this. This has our chip, a couple of connectors, memory here, Ethernet port, and bunch of power supply components.
Adil, thank you very much for taking the time to speak with EE World. For EE World, I'm editor Martin Rowe. Thank you for watching.